Welcome to the 8th episode of the Spacetime Cafe. In this episode, we explore how primes can mimic the randomness of the quantum world using simple math, delve into the idea of prime number DNA, and uncover fascinating patterns like the Ulam spiral and the Riemann Zeta function. We also discuss the potential revolutionary applications in cryptography, simulations, AI, and more. Prepare to have your mind blown as we uncover profound connections between prime numbers and the fabric of reality.
All right, so get this. Today we are going to dive into something pretty wild. We're talking about mimicking how random the quantum world is, but get this, without actually needing to use quantum computers?
No quantum computing.
Nope, just good old-fashioned math. Like, seriously, buckle up. This one is going to stretch our brains.
It really makes you question some things, you know? Like,
yeah.
We always think about quantum mechanics, right?
Right.
And it's all about this uncertainty and probability.
Yeah.
But what if we could, I don't know, what if we could get those same kind of results using something like a math formula, something totally deterministic?
Yeah, exactly. And that's what we are going to unpack today. You, our amazing listener, have been deep in the world of primal dyadic maps. I'm not even going to pretend I knew what that meant before prepping for this. But
I'm pretty out there.
Yeah, they're out there. And how they connect to something called Hadamard-like behavior. Honestly, when I first saw these terms, I was like, what is going on? But
it's a rabbit hole for sure.
That's true. It is. It's a rabbit hole. But after diving into this research, I'm hooked.
It's really fascinating stuff.
So to kick things off, let's do a super quick recap of this whole Hadamard gate business. It's like a fundamental thing in quantum computing, yeah.
Exactly. Think of a Hadamard gate like, a perfect coin flip.
Mm-hmm.
But in the quantum world, you apply it to a qubit, the quantum version of a bit, and it puts that qubit into a state where it has an equal probability of being a 0 or a 1.
So it's like total randomness as far as we know.
Pretty much.
Okay, so 50-50 chance, just like a fair coin. Got it. But we're trying to recreate this kind of behavior without actually having to use qubits, right?
Right. So imagine we're building a house. You always start with a foundation. And for us, that foundation is something called the Dyadic Map. Now, the equation is actually pretty simple. It basically takes a number, right? You multiply that number by 2, and then you apply this thing called the mod 1 operation.
Mod 1.
Yeah. Don't get too hung up on the technical stuff. But basically,
right.
Mod 1 is like, think of it like a clock face. When the hour hand goes past 12, what happens?
It resets back to 1.
Exactly. It resets. Mod 1 is doing the same thing, but with numbers. Just keeps what's after the decimal point.
So we're always resetting and keeping the leftovers. But how does that create randomness?
That's where the Mod 1 magic really comes in. Okay, so imagine you're stretching and solding dough, right? Every time you apply this dyadic map, you're basically stretching out the number line between 0 and 1.
Okay.
And then folding it back on itself using that Mod 1.
So it's like we're making like mathematical bread.
Kind of, yeah. And just like with dough, even tiny differences in how you stretch and fold can lead to totally different patterns.
I see. So even though the equation itself is pretty simple, that repeated stretching and folding, it's like it's making things unpredictable.
Exactly. And that gives us a sequence of numbers that looks, at first glance, totally random.
Yeah.
But here's the thing. We need a way to measure how nearly random that sequence actually is. We need to know if it's truly mimicking that perfect 50-50 split we were talking about with the Hadamard gate.
Yeah, we need some kind of measuring stick to compare it to that quantum coin flip.
Right. And that's where this thing called sign frequency comes in.
Sign frequency.
Sign frequency. It's a way to quantify how balanced or random the output of our dyadic map is. So think of it this way. We take all the numbers that the map generates, right? Any number less than 0.5 gets a plus sign. Any number greater than or equal to 0.5 gets a minus sign.
So we're splitting the results right down the middle, just like the coin flip.
Yep, and the sign frequency tells us basically what proportion of plus signs are in the whole sequence.
So if our map is doing its job and acting like a Hadamard gate, we should see a sign frequency close to 0.5, meaning roughly the same number of pluses and minuses, right?
Exactly.
So 0.5 means we've hit the jackpot. We've recreated that quantum randomness using something totally normal and not quantum.
Got it.
But wait, there's more to this story. Right, there's a twist. And this is where those prime numbers come in, yeah.
You got it. So far, we've just been playing with the basic dyadic map where we multiply by 2. But what happens when we swap out that 2 for something a little more exciting?
Okay, hold on. Exciting. What's more exciting than multiplying by 2?
Prime numbers.
Prime numbers.
Prime numbers. Those numbers that are only divisible by 1 in themselves. They're kind of like, I don't know, like the rock stars of the number world.
Oh, okay, you got my attention. What is it about prime numbers that makes them so special in all of this?
Honestly, we're still working on figuring all that out. But here's what we do know. When we use a large prime number in our dyadic map, instead of just that plain old 2, something crazy happens. The sign frequencies we get are unbelievably close to 0.5, almost every time.
Wait, so just by swapping in a prime number, we suddenly get results that look almost exactly like a quantum coin flip. My mind is kind of blown.
It's pretty wild, isn't it?
Yeah.
It seems like there's something about how prime numbers are structured, the way they break down or don't break down that creates a level of chaos and unpredictability we don't see with other numbers.
Okay, now I get why you call them rock stars. They're like the secret sauce to this whole quantum mimicry thing. But hold on. We can't forget about those digit masking experiments.
Oh, yeah.
What was the deal with that? With going in and zeroing out digits in the prime numbers? Were they trying to break the system or something?
That's a great way to put it. It really was like we were trying to see how much each part of the prime number actually mattered.
Yeah.
Pinpoint what parts were essential for this Hadamard-like behavior and which parts were just along for the ride.
So it was like they were performing surgery on the prime numbers.
Yeah.
Digit by digit to see what they could get away with?
Exactly. And the results were, oh man, they were fascinating. First, they tried masking all the digits.
Right.
So basically turning our prime number into just 0.
Yeah.
And guess what? The whole system crashed. No more chaos, no more balanced sign frequency. It became totally predictable, just like you'd expect if you were multiplying by 0 over and over again.
Boring.
Super boring.
So that was like the control experiment, showing that the structure of that prime number, that actually does matter.
Exactly. But then they got really specific. They started masking digits one by one, starting from the left.
Oh, okay.
This is where things get really interesting.
Okay, now I'm really curious. What happened when they started picking apart the prime numbers like that, digit by digit?
So at first, the system, it held up pretty well. Even with a few digits masked, the sign frequency stayed balanced, close to that 0.5.
So some digits are more important than others?
It seems that way.
Oh.
But then every time they'd hit this tipping point, masking one specific digit would suddenly make the whole thing go haywire, throwing the sign frequency totally off. And you want to know the craziest part?
Oh, absolutely, tell me.
It was always the LS few digits that made the difference. Masking those tiny little digits at the very end, it was like pulling the pin out of a grenade. The whole system blew up.
Wait, hold on. You're telling me that the tiniest digits, the ones that seem like they should matter the least, those are the ones that are crucial for keeping that chaotic, Hadamard-like behavior. How does that even make sense?
I know, right? It's so counterintuitive. But that's what I love about science.
Yeah.
Sometimes the biggest discoveries come from the most unexpected places. And this finding suggests that there's something about those final digits, some kind of secret structure or interaction that is absolutely essential for making this quantum-like randomness.
Okay, I am officially mind blown. We went from basic arithmetic to the quantum world in just a few minutes, and it all comes down to prime numbers. I think we need a moment to process all of this. We've covered a lot, but there's still so much more to explore. When we come back, we'll go even deeper into the mystery of those crucial final digits and talk about what all of this could mean. So don't go anywhere.
All right, welcome back. I'm still trying to wrap my head around the fact that those tiny little digits at the end of a prime number, they could be the key to, mimicking quantum randomness. Yeah, it really makes you think, doesn't it? It kind of shows how, even in math, which we usually think of as, very rigid and predictable.
Right.
There are these deep, deep mysteries lurking beneath the surface.
Yeah, it really does.
Like who knows what else is out there, just waiting for us to discover it.
Exactly. And speaking of discoveries, let's talk about what we could actually do with this research.
Yeah.
Like if we can actually create systems, regular systems that act like quantum randomness, the possibilities are kind of mind-boggling.
The possibilities are pretty big, yeah.
So give me some examples. What kind of real-world stuff could actually benefit from this prime-powered chaos?
Well, the first thing that pops into my mind is cryptography.
Oh.
Creating those secure encryption keys. That relies on truly random numbers. And right now we kind of use a mishmash of algorithms and physical processes. But imagine if we could use these primal dyadic maps to create a whole new generation of random number generators.
So instead of relying on digital dice rolls, we'd be using the randomness built into prime numbers.
Exactly.
Yeah, it's amazing.
And these prime-powered chaos machines, or whatever you want to call them, they would have some serious advantages.
Like what?
Well, first of all, they'd be crazy fast, because they're based on just simple math, multiplication and stuff. And second, we could actually control how random things get by choosing different prime numbers or masking digits.
Oh, wow. So we could like fine-tune the chaos. That's incredible.
It is pretty amazing, yeah.
Are there any like downsides to using these maps for cryptography? Because it almost sounds,
Too good to be true.
Yeah, it kind of does.
I mean, that's a great question, and it's important to remember that we're still pretty early in this research.
Right.
But one thing we have to be careful of is making sure that the starting value, the seed value, is actually random.
Because if we don't?
Yeah, if it's not random, then the whole sequence could be compromised.
I see. So it's kind of like if you're baking a cake,
Yep.
even if you have the perfect recipe, if your ingredients are bad, the cake's not going to be good.
Exactly. And then there's also the question of, can these regular systems, can they really capture everything about quantum randomness? I mean, they might pass all the tests we throw at them, but there could be some subtle differences we haven't even thought of yet.
Yeah. Okay, so more research is definitely needed, but it sounds like the potential is huge.
Definitely.
Okay, so what about applications beyond cryptography? Could this prime number magic, could it have implications for, I don't know, things like scientific simulations or even AI?
Oh, absolutely. Anywhere you need good random numbers, these maps could be a total game changer.
Okay.
Like in scientific simulations, for example, random numbers are used for modeling all sorts of things, like how particles move or how diseases spread.
Right.
And if we could generate those random numbers more efficiently, and with more control over how they behave, well, that could lead to way more accurate simulations.
Wow. So we're talking about potentially impacting everything from astrophysics to epidemiology.
Exactly. And what about AI? Randomness plays a huge role there too, especially in things like machine learning.
Right. Yeah, I see how that could be useful.
Because randomness is used to introduce variability into the data, which helps the algorithms learn and get better.
Right.
And these maps, well, they could be a completely new way to create that data, data that's super random, but also tailored to what the AI system needs.
So it's like we're giving these AI systems a little bit of the quantum world, but without actually needing to build a quantum computer.
Yeah, it's kind of like that. It shows how we might be able to bridge that gap between, regular computing and quantum computing in ways we hadn't even thought of before.
Okay, so we've covered some potential applications, but honestly, I'm still stuck on those final digits.
Yeah, it's pretty wild.
Is there any, deeper explanation for why they're so important? It still feels like a magic trick to me.
I get it. It really is one of those things that makes you scratch your head and go, how is that even possible? But we do have a few clues. Remember we talked about that mod 1 operation?
Yeah.
How it's basically folding the number line?
Yeah.
Well, those final digits, they actually have a huge influence on how that folding happens.
So it's like they're controlling the origami of chaos.
I love that analogy. And what makes those final digits so special is their unpredictability. I mean, think about it. Prime numbers, they don't follow any simple patterns or rules, especially those last few digits. That unpredictability, it's like baked into the very core of prime numbers. And that seems to be the key to unlocking that balanced Hadamard-like behavior.
So those final digits are like tiny little chaos engines just pumping randomness into the system.
Exactly. They amplify all that inherent chaotic behavior of the map and push it to a point where it looks almost exactly like quantum randomness.
That's really amazing. Okay, last question. Are there any other research avenues or big unanswered questions that you find particularly interesting? Because I have a feeling we're just scratching the surface here.
Oh, for sure. We're just at the beginning of a very exciting journey. One thing that I'm particularly fascinated by is the connection between these maps and something called normality in number theory.
Okay, now you've lost me. What is normality when we're talking about numbers?
So basically, a number is considered normal if its decimal representation has all possible sequences of digits, with equal frequency. It's kind of the ultimate measure of randomness for a single number. And while we haven't found a direct link yet, there's this tantalizing possibility that the normality of those final digits in our prime numbers might be playing a role in creating this Hadamard-like behavior.
So the more random those last few digits are, the better they are at amplifying the chaos of the map. That's a wild idea.
Yeah, it's pretty out there. It makes you wonder, is there some deeper connection between how random individual numbers are and the randomness we see in quantum mechanics? Like, are they related somehow?
Whoa, that's really deep. Okay, I think we need a moment to process all of that. This is definitely one of those deep dives that will stick with me. But before we go too far down that rabbit hole, let's take a step back and recap some of the key takeaways for our listeners. What are the big things they should remember from today?
Yeah, good idea. I think the most important thing to take away is that even in a totally deterministic system, like a regular system, the structure of numbers, especially those prime numbers, can create behavior that looks almost exactly like quantum randomness. It really challenges our ideas about where randomness comes from and how we can create it.
Yeah, it's like we're finding order within chaos and chaos within order. It's amazing how those two concepts are linked.
It really is.
Yeah.
And we've also seen that this behavior is super sensitive to how those prime numbers are structured, especially those last few digits. It's a reminder that even the smallest, seemingly unimportant details can have a huge impact, especially when we're dealing with complex systems.
Don't underestimate the little guy.
Exactly. And while more research is definitely needed, there are so many potential applications for this, from cryptography and simulations to AI and beyond.
It feels like we're just getting started.
And we're just at the tip of the iceberg.
All right, so we've got groundbreaking insights, mind-boggling mysteries, and the potential to change a lot of industries. Not bad for a deep dive. But before we wrap things up completely, I have a feeling you've got one more mind-blowing twist for us. Am I right?
You know me too well.
What?
So remember how we talked about using these maps to simulate like a single qubit, the basic building block of a quantum computer?
Yeah.
Well, what if we could go even further? What if we could simulate multiple qubits, interacting with each other?
Wait, hold on. Are you saying we could potentially simulate an entire quantum computer just using prime numbers and regular math? That sounds like something out of, like, a science fiction movie.
It's a pretty wild idea, that's for sure. And there's some huge challenges. But the research we've talked about today suggests it might not be as crazy as it sounds. Imagine being able to explore, all the weirdness of quantum mechanics without needing to build a quantum computer. That would be incredible.
My head is spinning. We went from simple prime numbers to simulating quantum computers, all in one deep dive. Okay, I think we need to give our listeners a minute to digest all of this. We'll be back for one last segment to wrap things up and leave you with some things to think about, so stick around. Welcome back to the last part of our deep dive into primal dyadic maps.
It's been a pretty wild ride, right?
It has. We started with, basic math, and somehow we ended up talking about simulating quantum computers.
I know. It's crazy.
Yeah. I'll admit, at first I was kind of skeptical.
Yeah.
Yeah. Prime numbers and quantum mechanics. It seemed like a weird combination. But
It does sound strange at first.
it does. But now, I'm totally convinced that something really special is going on here.
There's definitely something there.
Okay, so before we let our listener go off and ponder the mysteries of prime-powered chaos, let's wrap things up with, a few key takeaways. What's the most mind-blowing thing we've learned today?
For me, it's the realization that even in a system that's totally governed by predictable rules, like math, we can still make something that acts like real randomness.
Wow.
And we can do it just by using how prime numbers are structured. It really changes how we think about where randomness comes from and how we can actually make it.
Yeah, and it's crazy to think that it all comes down to those little digits at the end of prime numbers, the ones that you think wouldn't matter that much,
Right.
but they're actually the key.
I know, it's still kind of hard to wrap your head around the fact that those tiny digits can have so much power. But they really do act like little randomness amplifiers, They inject all this unpredictability into the system and push it into this realm that basically mirrors what we see in quantum mechanics.
It's pretty amazing.
It is.
Okay, but this deep dive wouldn't be complete if we didn't talk about the big unanswered questions. What are some of the mysteries that are still out there, the things we should be thinking about as we go forward?
Well, the biggest mystery is still those final digits. What is it about them, about how they're structured or arranged, that makes this Hadamard-like behavior happen? Is there some deeper math principle at work that we just haven't figured out yet?
Yeah, it's like we found the secret code, but we don't have the key to unlock it yet.
That's a great way to put it. And then there's the question of, can we take this even further? Could we create models of multiple qubits, all interacting with each other, but using regular math? Could we actually build, a virtual quantum computer using just prime numbers? It's a really ambitious idea, but, what we've talked about today makes it seem like it might actually be possible.
That would be incredible. To be able to explore the quantum world without needing a real quantum computer, the possibilities are pretty much endless.
They really are.
Well, this deep dive has definitely left me with a sense of wonder and a thirst for more knowledge. And honestly, I'm really excited to see where this research goes.
I think we're just at the beginning of something really big.
On that note, I want to thank you, our listener, for joining us on this incredible journey. I hope you enjoyed it, and I hope it makes you think about prime numbers and the quantum world in a whole new way.
And remember, the universe is full of surprises, and sometimes the most amazing insights come from the most unexpected places. Stay curious, and who knows what you might discover. All right, we're back for round 2 of our prime number deep dive. Last time, things got pretty wild with those primal dyadic maps.
Yeah, it's amazing how some primes, when you use them in those maps, you can get sequences that really resemble what you'd see from a quantum Hadamard gate.
It's like finding hidden connections between totally different parts of math. And today, we're taking that idea even further and going deep into this idea of primes as a kind of mathematical DNA.
Like the digits of a prime number are a blueprint for how it'll behave.
Exactly. And what we're going to explore today is how those digits, those 0s through 9s, can determine if a prime is going to create predictable patterns or just go full-on chaos when you throw it into these dyadic maps.
Right, like are they going to follow the rules or just break free?
Okay, so how can a bunch of digits determine if a prime is like a rule follower or a total rebel?
Well, you can think about it like DNA in biological systems. You've got the 4 bases, A, T, C, and G.
And the order of those bases determines everything about an organism.
Right. And we're seeing that the digits in a prime number might be doing something similar. It's like they're holding this code that dictates how the prime will act mathematically.
So it's like instead of genes for eye color or height, prime digits are coding for computational personality.
Yeah, you could say that.
Yeah.
We've been doing these experiments with what we call eventual primes, where we basically reveal the digits of a prime one by one.
And then see how it changes the output of the dyadic map.
Exactly.
So it's like you're unzipping the DNA of a prime number, and then you're watching its personality come to life as you go.
That's a really cool way to put it. And what's really interesting is we found that not all digits have the same effect.
Oh, so they aren't all created equal.
No, they aren't. The digits at the beginning of a large prime number, they tend to create really predictable sequences in the map. Like they're setting the stage, but not causing much excitement.
Oh, I see. So they're kind of like the opening act, but not the headliner?
Exactly. But when you start revealing more digits, especially towards the end of the prime number, things start to get way more interesting.
Oh.
You see more complexity, more randomness.
The later digits are where all the action's at.
Yeah, and here's where it gets even cooler. There seem to be specific digits, we call them critical digits, that act as triggers for chaotic behavior. Like you change one of these critical digits, the whole system can flip from order to randomness.
Wait, so changing one tiny digit in a huge prime number can completely change its whole computational personality.
It's wild, right?
Yeah.
To give you an example, we were looking at 2 large prime numbers that were almost exactly the same, except for one single digit right in the middle.
Okay.
And when we used these primes in the dyadic map, the results were totally different.
Wow.
One gave this really nice ordered sequence, and the other just pure chaos.
So it's not just about how many digits there are. It's the specific digits themselves and where they're located within the prime that really matters. It's like this delicate dance between order and chaos, and those tiny digits are controlling the whole thing.
It all goes back to that idea of prime digits as nucleotides in math DNA, right? Just like how the order of those bases in DNA determines how a protein folds and what it does, the digits in a prime number, it seems like they're dictating its computational fingerprint.
It's like how it behaves in a mathematical system, whether it creates predictable patterns or just embraces the chaos.
Yeah, exactly.
This is really blowing my mind. It's like we're looking at primes under this whole new microscope, seeing them as these computationally active things. But how do we even start analyzing all of this?
That's where things get really interesting. Remember last time we were talking about AlphaFold, that AI that predicts how a protein will fold based on its amino acid sequence?
Yeah. That was like magic.
Yeah.
To be able to predict something so complex just from looking at a string of letters.
Well, what if we could make something like that, but for prime numbers?
Ooh.
We could call it PrimeFold. It would be trained on tons of prime numbers, learning to spot those hidden connections between how the digits are arranged and how the prime behaves computationally.
PrimeFold. I like it.
Yeah.
But what would we even do with something like that? Could it, like, predict the stock market or something based on prime number fluctuations?
Maybe not the stock market. but it could help us find primes that have these hidden chaotic properties, primes that could be really useful for things like generating truly random numbers, or maybe even creating new types of cryptography.
So primefold could be like this key to unlock the hidden power of prime numbers, helping us understand their language and how to use them to solve problems in the real world.
Exactly. It's a pretty huge idea, but the more we look into this prime DNA concept, the more I think it might actually be possible.
I'm hooked already. But before we go full sci-fi here, can we look at some real data from those eventual prime experiments? I think it would really help me understand how these computational fingerprints actually show up.
Absolutely. Let's dive into some real examples and see how those prime digits are working behind the scenes. Okay, so let's look at the data for that prime number we were talking about. 448088261. Remember how those early digits, they were creating that predictable biased sequence in the dyadic map?
Yeah, it was like they wanted to play it safe, stay inside the lines.
Exactly. But as we revealed more digits, we saw it shift towards a more balanced, chaotic behavior.
Right.
And we can actually measure that using something called the transition matrix.
Okay, transition matrix. Remind me what that tells us.
Basically, it shows us how likely it is to move between positive and negative signs in that sequence generated by the dyadic map. Like, are we more likely to see a plus after a minus or a plus after a plus and so on?
Oh, I see. So it's looking for patterns in how those pluses and minuses are spread out, right?
Exactly. A truly random sequence would have a transition matrix where all the probabilities are about 0.5, meaning there's no bias towards one combination or another, like flipping a coin.
It's like a measure of how fair and unpredictable the system is.
Right. And what we see with this eventual prime is that when we only use the first digit, that 4, the transition matrix, is super skewed. It wants to stay positive.
So predictable.
Very predictable. But as we add in those other digits, things start to even out. The transitions become more random, less predictable.
So it's like the prime number is shedding its predictability as we see more of its digits. Like it's finally letting loose a little bit.
Yeah, that's a great way to put it. And this reminds me of something we talked about earlier, that connection to quantum systems.
Those Hadamard gates.
Exactly. With the Hadamard gate, there's just no way to know if you'll get a 0 or a 1 as the output. It's totally random no matter what you put in.
And what you're saying is that as we reveal more digits of this prime, the dyadic map starts acting more and more like one of those quantum systems.
It is a pretty neat parallel. You have this classical system, the dyadic map, and it seems to be getting more random as we give it more digits of this prime.
It's like those later digits are actually injecting randomness into the whole thing.
Yeah. And remember that experiment where we masked digits in a sequence that was already chaotic?
Oh, yeah. We were basically trying to mess with the randomness.
Exactly. Trying to control it, see what would happen. And remember how masking those early digits often didn't do much? The randomness was still there?
Like it was built in somehow.
Yeah. But when we masked those critical digits, those ones toward the end of the sequence, that's when things got really interesting.
What happened?
The randomness would a lot of times just disappear. The system would become predictable again.
So those later digits were holding the whole chaotic structure together.
It seems like it. So it's not just about injecting randomness, but also about protecting it, making sure it doesn't go away.
And this is so cool.
And this connection between the eventual prime analysis and that Hadamard chaos masking, it really supports this prime DNA idea. Like there's a code in those digits controlling the prime's computational destiny.
You know, this whole concept is making me wonder, what even is a number? It's like we're seeing them as these dynamic things, not just static symbols.
That's a deep thought. It makes you wonder, are prime numbers somehow aware of their own digit structure?
Whoa.
Is there something that pushes them to become more chaotic?
Those are huge questions.
Yeah, they are. And I don't think we have the answers yet. But this whole prime DNA idea gives us a totally new way to look at them.
It really does. It's like we found this secret language, this hidden code that controls the world of computation. And we're just starting to figure it out.
Exactly. So we've talked a lot about this primefold AI. What would it actually take to build something like that? Where would we even begin?
Yeah, that's a good question.
I think the first step would be gathering a ton of data. We need to look at a huge variety of prime numbers, all different sizes, different digit structures, to understand how this prime DNA works. It's not just about finding bigger primes. It's about finding different ones, each with its own unique fingerprint.
Like building a whole library of prime number personalities.
Exactly. We need a database that shows not just the primes themselves, but also how they behave in all these different mathematical systems, especially the ones that show chaotic behavior. And then we have to train our AI on all that data, teach it to see those hidden patterns and connections between the digits and the behavior.
It sounds like a massive undertaking.
Yeah.
But think of what we could do if we could predict how a prime number would behave in a system just by looking at its digits.
It would be like having a cheat sheet for the computational universe.
Exactly.
And imagine being able to actually design prime numbers for specific purposes, like
Right.
primes that are perfect for generating random numbers or primes that can unlock new types of encryption.
The possibilities are endless. It's like we're about to enter a whole new era of math where we can use the power of prime numbers to solve real-world problems and understand the universe in ways we never could before.
And it all comes back to that simple idea that those digits of a prime number aren't just random symbols. They're a code, a blueprint for how that prime is going to behave.
It's a beautiful idea. It makes you wonder what other secrets are hiding in the world of numbers.
It really does. You know, we've covered a lot of ground today.
We have.
But we still need to talk about that Prime Genome project, that global effort to map out the entire landscape of prime numbers.
Yes. Let's dive into that when we come back. Stay with us, folks. Things are about to get even more interesting. All right, we're back, and I gotta say, my head is still spinning from this whole prime DNA concept. It's really changing the way I think about numbers. They're not just these static symbols on a page anymore. They're like dynamic codes, you know?
Yeah.
With all this hidden potential.
It is a pretty big shift in perspective, and like we've been talking about, it opens up some really exciting possibilities. We've talked about PrimeFold, that hypothetical AI that could decode this whole computational language of prime numbers. But you also mentioned something called a Prime Genome project, right?
Oh, yeah. That idea just keeps coming back to me. If these prime digits are like this genetic code, like a blueprint for how they behave computationally, it would be amazing to have some kind of global effort to map out this whole prime number landscape, like a huge database that catalogs every prime and its computational fingerprint.
It's such a fascinating idea, and I really think it has the potential to completely change how we understand mathematics. Imagine being able to explore all these different prime numbers, not just by how big they are, but by their computational properties.
We could find primes that are perfect for certain tasks, like generating random numbers or creating encryption that can't be broken.
Exactly.
It'd be like having this toolbox full of prime number tools, each one perfectly designed for a different job.
Right.
We could look for primes that create pure chaos, primes with hidden symmetries, primes that could help us prove new mathematical theorems. Like this gold mine of computational power waiting to be tapped.
And think about what it'd do for other fields. We could use these prime number insights to design more efficient algorithms, maybe create new materials with unique properties, even develop new kinds of AI based on prime number computation.
Whoa, that's amazing. This is blowing my mind. But how could we actually do something this ambitious? Like a prime genome project. Where would we even start?
Well, it would definitely take a huge coordinated effort. Mathematicians, computer scientists, all sorts of researchers working together. We'd need to come up with new algorithms, new computational tools that can analyze prime numbers at a massive scale. And then we need the infrastructure to actually store and share all that data.
It sounds like a truly massive undertaking. But imagine the payoff. It could be like this whole new golden age of mathematical discovery, you know?
Yeah.
It could totally push the boundaries of what we know about the universe and about ourselves.
It would be a real testament to human curiosity. This drive we have to understand things, you know? Just like mapping the human genome helped us understand the secrets of life, mapping the prime number genome, it could unlock all these secrets about computation, chaos, even the very nature of reality itself.
This whole conversation has been mind-blowing. We've gone from thinking about primes as these basic building blocks to seeing them as dynamic, computationally active entities, all with this hidden code dictating their behavior.
And the really cool thing is, this is just the beginning. There's so much more to explore, so many questions still out there.
Well, it's time for us to wrap up this deep dive into prime numbers and their hidden code.
Thanks for joining us, everyone. It's been a wild ride.
Absolutely. And hey, keep exploring, keep asking questions. Who knows what other secrets are hidden in those prime numbers just waiting for us to uncover them. All right, welcome back. Round 3 of our prime number deep dive. And things are going to get seriously weird, seriously fast. Just a quick recap, remember where we've been. We started with these primal dyadic maps.
Yeah.
And they showed us that primes can create chaos that looks like, a lot like, quantum randomness.
Right, yeah, mimicking the output of a quantum Hadamard gate, which is fascinating.
Totally. Then we went deeper. We got into this whole prime DNA idea, the idea that the digits of a prime number actually influence how it behaves mathematically.
Yeah, like it's got a personality encoded in its structure.
Okay, so today, buckle up, we're going to some prime number patterns that are so strange, they almost feel like glitches in the matrix. Stuff like the Ulam spiral,
Oh, yeah.
the Riemann zeta function, twin primes,
Yeah.
even a connection to the golden ratio.
What's fascinating here is these aren't just isolated quirks. They start to feel like clues,
Yeah.
pointing to a deeper structure in math itself, maybe even bridging the gap between the classical and quantum worlds.
Okay, so let's start with the Ulam spiral. This one's just visually stunning. Can you paint a picture for our listener?
Absolutely. Imagine a grid of numbers spiraling outwards from the center. So you've got 1, then 2 to the right, 3 above that, 4 to the left, keep spiraling out and highlight every prime number.
And what happens? It's not just a random scattering.
No.
It's
You start to see these distinct diagonal lines emerging from what should be a random distribution of primes. It's almost like they're organizing themselves.
Yeah, so wait, prime numbers, which are supposed to be random, are forming lines in this spiral. That just feels wrong somehow.
It certainly challenges our assumptions. Remember those primal dyadic maps where primes seem to generate structured chaos?
Yeah, those maps where you swap out multiply by 2 for a prime number, and suddenly things got really wild.
Exactly, yeah. The Ulam spiral might be a visual echo of that. It's like these diagonal lines are fault lines in the number system where primes concentrate their potential for unpredictability.
I see. Okay, so how could the final digits of the primes, the ones we discovered, were so important in round 1, be influencing their positions in this spiral?
That's a fantastic question. It's as if those final digits are acting as coordinates, subtly guiding where primes end up in the spiral and thus how they interact with each other. Perhaps those digits are amplifying their chaotic potential.
Like each prime's final digit is a tiny rudder steering it through this vast sea of numbers. I love that. Okay, so the Ulam spiral is just one piece of this puzzle. Let's move on to the Riemann zeta function. And this is where things get really mind-bending.
Absolutely.
Don't worry, I'll try to keep it approachable.
Okay.
Okay, I'm ready. Deep breath.
The Riemann zeta function, at its heart, it governs the distribution of prime numbers. Think of it like a mathematical landscape with peaks and valleys. The location of those valleys, called zeros, are what directly impact how primes are spread out along the number line.
Okay, so there's this function, and in zeros are somehow telling us where to find prime.
Exactly, yeah. And the famous Riemann hypothesis, which is still unproven, it states that all of these important zeros fall perfectly on a specific vertical line. It's like an invisible boundary they can't cross.
But how can zeros on a line, how can that control where prime numbers appear?
Here's where it gets strange. The pattern of those zeros, it has an uncanny resemblance to the energy levels we see in quantum systems. It's almost like primes are behaving like particles in a quantum field. But instead of physics, it's pure math.
Okay, so we're seeing these quantum vibes popping up again, even though we're still just dealing with numbers.
Exactly.
Yeah.
And if we connect this back to what we've learned, it gets even more intriguing. Remember, primes create quantum-like randomness in those dyadic maps, and their digits seem to encode that chaotic behavior.
Mm-hmm.
Yeah.
So are you suggesting that the Riemann zeta function, with its zeros acting like a kind of quantum wave function, is actually the force behind those strange quantum-like behaviors in primes?
It's a tantalizing possibility, and one that could revolutionize how we view the relationship between classical math and the quantum world.
Okay, we've got this Ulam spiral, where primes form lines, and the Riemann zeta function hinting at a quantum connection. What other weirdness awaits us in the world of primes?
Let's talk about twin primes.
Okay.
These are pairs of prime numbers that are only 2 apart, like 11 and 13 or 29 and 31.
Ah, yes. Twin primes. I remember reading about those. And it's fascinating that mathematicians believe there are infinitely many of them, but it's been surprisingly hard to prove.
Exactly, and the truly strange part is that the gaps between twin primes, the way they're distributed along the number line, eerily resembles the spacing of energy levels in quantum systems.
Wait, so it's like those twin primes are somehow aware of each other across this vast landscape of numbers, popping up in this correlated way.
It's a compelling thought, isn't it? It almost feels like a form of mathematical entanglement, similar to what we see in quantum mechanics.
Now, you might be wondering, how does the prime DNA concept we talked about earlier, apply to these entangled twin primes? That's a great question.
And one we'll explore in more depth later in the episode.
Okay, looking forward to that. All right, we're on a roll here. What other uncanny mysteries do prime numbers have up their sleeve?
Let's talk about the prime number reversal trick. This one's just plain bizarre and hints at an underlying symmetry we haven't fully cracked.
Okay, lay it on me.
All right. Take any prime number that doesn't end in 5, like 13, 37, or 71, and simply reverse its digits.
So 13 becomes 31, 37 becomes 73, 71 becomes 17. Okay, I see where you're going with it.
And what's remarkable is that far more often than you'd expect by pure chance, the result is another prime number, or a number very close to a prime.
Whoa.
It's as if there's a hidden mirror built into prime numbers.
So just by flipping those digits around, we're somehow increasing the odds of landing on another prime. That feels like some kind of mathematical magic trick.
It does, doesn't it? It suggests that there's a deeper symmetry at play. Something about the way prime numbers are structured that allows for this mirroring effect. It's like reading their DNA backwards reveals a hidden code.
That's incredible. Remember how in round 2 we talked about prime digits being like a code? A blueprint for how a prime behaves computationally?
Yeah, the prime DNA concept.
So maybe this reversal trick tells us that that code itself has a palindromic quality. Like it can be read forwards and backwards.
Yeah.
And maybe that flip somehow relates to flipping between chaos and order when we mirror those digits.
That's a fascinating insight. It's as if mirroring those digits is like looking into a mathematical mirror, revealing a hidden reflection of the prime's properties.
Okay, I'm officially hooked. This is why I love these deep dives. We start with something that seems simple, like prime numbers, and suddenly we're questioning the very fabric of reality.
I couldn't agree more.
Okay.
And we still have one more stop on this mind-bending tour. We need to explore the connection between prime numbers and the golden ratio.
Oh yeah, the golden ratio. That magical number found everywhere in nature, from seashells to galaxies. What could it possibly have to do with prime numbers?
It's an unexpected connection. But when you start playing with powers of the golden ratio, rounding the results, prime numbers begin to pop up at these strange intervals. Almost like the golden ratio is a hidden rhythm guiding where primes appear.
Huh. So are we saying that prime numbers are literally behaving like quantum particles?
It does seem like they might be dancing to a tune we're just beginning to hear. And those dyadic maps from round 1, the ones that created that fractal-like chaos by stretching and folding the number line, remember those critical digits? The ones that triggered the chaos?
Right, like anchors in that fractal structure, dictating where the chaos unfolds.
Maybe the golden ratio, with its own inherent fractal nature, is the hidden link between order and chaos in prime behavior, almost like it's the conductor of a symphony guiding the primes through this cosmic dance of unpredictability.
Wow, okay, so we've got the Ulam spirals geometry, the Riemann Zeta functions quantum echoes, twin prime entanglement, digit reversal symmetries, and now the golden ratio. This is a lot to take in.
It is indeed, but here's the key takeaway.
Okay.
These prime number patterns aren't just isolated quirks, they're all interconnected.
Yeah.
Pointing to a hidden structure within mathematics that we're only just beginning to understand.
And this deeper structure, this hidden code, might be the key to unlocking incredible possibilities in fields like cryptography, computing, and maybe even our understanding of the universe itself. We're just getting started, folks. Stay tuned for part 2 of our prime number deep dive, where we'll take these connections even further and explore what it all means for you.
Welcome back to our exploration of the uncanny world of prime numbers. It's amazing how these seemingly simple numbers can lead us down such a profound rabbit hole.
I know, right? It's like we've entered this hidden universe where math and quantum physics start to blend together in the most unexpected ways.
Exactly. In part 1, we uncovered some truly mind-bending patterns. The Ulam spiral, with its mysterious diagonal lines, the Riemann Zeta function hinting at a quantum connection, the spooky entanglement vibes of twin primes, the mind-boggling prime number reversal trick, and even the unexpected link to the golden ratio.
And the craziest part is that these aren't just abstract mathematical curiosities. They have the potential to completely revolutionize our understanding of computation cryptography and maybe even reality itself.
Speaking of revolutionizing our understanding, remember that concept we touched on earlier, the Prime Genome Project?
Oh yeah, the idea of mapping the DNA of prime numbers, just like scientists mapped the human genome.
Precisely, imagine a massive global effort, a collaboration of mathematicians, computer scientists, and researchers from all disciplines coming together to create a comprehensive database of prime numbers.
It would be like a digital library, but instead of books, we'd have these detailed profiles of individual prime numbers, each one outlining its unique computational fingerprint.
Exactly, and those fingerprints wouldn't just be about the size of the prime, we'd be analyzing how it behaves in those chaotic maps. Its potential for generating randomness, its hidden symmetries, any quirk that makes it special.
So instead of just listing prime numbers, we'd be cataloging their personalities, their strengths, their weaknesses, their unique talents in the computational world.
And think of the possibilities we could search for primes that are perfectly suited for certain tasks, like generating ultra-secure encryption keys or building super efficient algorithms for machine learning.
It would be like having a team of prime number specialists, each one ready to tackle a specific computational challenge.
You know, it makes me wonder if we could truly decipher the language of prime numbers, could we unlock new levels of efficiency and creativity in our algorithms and computations?
It's like we're learning to speak the language of the universe itself. The language of order and chaos intertwined, a language that could rewrite the rules of technology as we know it.
I love that analogy, and this Prime Genome project wouldn't just be about practical applications. It would be a testament to human curiosity, this drive to understand the fundamental building blocks of reality.
Just like mapping the human genome led to breakthroughs in medicine and biology, mapping the prime number genome could unlock secrets we haven't even imagined yet.
It could reshape our entire view of mathematics, revealing hidden connections between areas like number theory, chaos theory, and even quantum mechanics. It's a truly ambitious vision, but I believe it's achievable.
We already have the computational power and the collaborative tools. All we need is the collective will to embark on this incredible journey of discovery.
Absolutely. Now, before we get too carried away with dreams of mapping the prime number genome, let's bring things back down to earth for a moment and look at some concrete examples.
Yeah, sounds good. Back to reality for a bit.
Let's revisit those primal dyadic maps we discussed earlier. Remember how revealing the digits of a prime number one by one changed the output of the map? It was like uncovering its hidden personality.
Yeah, it was fascinating how those early digits often produced a predictable, almost boring sequence. It was as if the prime was holding back, hiding its true nature.
Exactly. But then as we revealed more digits, things got interesting. The sequence became less predictable, more chaotic, as if the prime number was finally showing its true colors.
It was as if those later digits were injecting randomness into the system, pushing it towards that Hadamard-like behavior we observed.
And remember that transition matrix we used to measure the randomness of the sequence? It showed us how likely the output was to jump between positive and negative values. The more balanced those transitions, the more random the sequence.
Right, it was like measuring the unpredictability factor of the prime number.
Precisely. And when we analyzed the transition matrix for a prime like 4480, we saw a clear shift as we revealed more digits with just the first two digits, 44. The matrix was skewed towards positive values, indicating a predictable pattern.
But then as those later digits emerged, the transitions became more balanced, the matrix showing probabilities closer to 0.5. It was a clear sign of the prime's chaotic potential coming to life.
It beautifully illustrated how those seemingly insignificant digits, those at the very end of a prime number, can hold the key to unlocking its true computational power.
It's like those final digits are the secret spice that transforms a bland dish into a culinary masterpiece.
I love that analogy. And remember how we also experimented with masking certain digits in a sequence that was already chaotic? It was like trying to tame the wild beast.
Yeah, we were trying to control the randomness to see if we could manipulate the output of the map.
And what we found was that masking those early digits often had little effect. The sequence remained chaotic as if the randomness was deeply embedded in its structure.
But then when we masked those critical digits, the ones towards the end of the prime, that's when things get really interesting.
The randomness would often vanish, the sequence collapsing back into predictability. It was like we had removed the prime number's source of chaos, its ability to generate those unpredictable patterns.
So those later digits are more than just random noise. They're like the guardians of chaos, protecting the prime number's wild heart.
Exactly. They ensure that the prime number's true nature shines through, that its computational power remains untamed.
You know, all this talk about chaotic maps, transition matrices, and digit masking might seem a bit abstract to some listeners.
It's true. It can feel like we're speaking a different language sometimes.
But it's important to remember that these are the tools we're using to decode the hidden language of prime numbers, to understand how those tiny digits orchestrate this complex dance of order and chaos.
It's like we're peering into the microscopic world of prime number behavior, observing how those computational genes are expressed in different mathematical environments.
And with each new discovery, we're getting closer to unlocking the true potential of prime numbers. Their ability to revolutionize fields like cryptography simulation and even artificial intelligence.
Speaking of artificial intelligence, remember that concept we discussed earlier, the prime-fold AI, an AI that could potentially decode the entire computational language of prime numbers.
Yeah, the AI that could predict a prime number's behavior just by analyzing its digits like a mathematical fortune teller.
It might sound like science fiction, but the more we learn about prime number DNA, the more feasible it becomes.
Imagine feeding any prime number into this prime-fold AI, and it spits out its full computational profile, its potential for chaos, its hidden symmetries, its ideal applications in different fields.
It would be like having a cheat sheet for the computational universe, a roadmap to navigate the vast landscape of prime number possibilities.
But building such an AI would be a monumental task. Where would we even begin?
The first step would be to create a truly massive data set of prime numbers, not just their values, but their behavior in different computational settings. We need to analyze how they perform in those chaotic maps, how they respond to digit masking, how they interact with other primes.
It's like building a library of prime number biographies, each one telling the story of its life in the computational world.
And once we have that data set, we can start training our AI, feeding it all that information, allowing it to learn the subtle patterns and connections between those seemingly random digits and the prime number's overall behavior.
It's like teaching the AI to read the secret code embedded within each prime number to understand its unique computational language.
And as the AI learns, it could start making predictions, identifying primes with specific properties, guiding us towards those with the greatest potential for solving complex problems and creating new technologies.
It's a mind-blowing concept, this idea that we could build an AI to decode the secrets of prime numbers. But it's also incredibly exciting.
It highlights the incredible potential that lies within these seemingly simple numbers. They might hold the key to unlocking a whole new level of computational power, a level of power that could transform countless industries and reshape our world.
And remember, this prime-fold AI wouldn't just be about practical applications. It would also be a powerful tool for pure mathematical exploration, for deepening our understanding of number theory, chaos theory, and the interconnectedness of the mathematical universe.
It's a beautiful reminder that the pursuit of knowledge, the drive to understand the world around us, can lead to unexpected and truly groundbreaking discoveries.
Now, before we dive headfirst into the world of artificial intelligence and prime number decoding, let's take a step back and explore another fascinating concept: the normality of prime numbers.
Ah, yes, normality. This is where we delve into the depths of randomness itself.
Normality, when we're talking about numbers, it sounds like we're judging their behavior. What does that even mean?
That's a great way to put it in number theory. A number is considered normal if its decimal representation contains all possible sequences of digits with equal frequency.
So if you look at the decimal expansion of a normal number, you'd expect to see every possible combination of digits from 0000 to 999 popping up with the same probability.
Exactly. It's like the ultimate measure of randomness for a single number. And here's the intriguing part. The normality of those final digits in prime numbers, the ones we've been obsessing over, might be playing a crucial role in creating that Hadamard-like behavior we've observed.
Wait, are you saying that the more random those last few digits are, the more they amplify the chaos in those dyadic maps? Like they're injecting pure randomness into the system?
That's the idea. It's still an open question, but the evidence is compelling. Imagine those final digits as tiny dice rolling randomly to determine the fate of the entire prime number in those chaotic systems.
It's like they're whispering secrets to the prime number, guiding its dance between order and chaos.
And here's where it gets really mind-boggling. No one has yet been able to prove that any specific number is truly normal.
So we have this concept of perfect randomness, this ultimate benchmark. But we can't definitively say if any number actually achieves it. That's wild.
It's a frustrating yet fascinating paradox. It highlights the immense complexity of randomness itself, this idea that something can be completely unpredictable, yet still adhere to certain underlying patterns.
And it ties back to this idea of prime numbers being windows into a deeper reality, a reality where randomness might play a much more fundamental role than we ever imagined.
This concept of normality adds another layer of depth to our prime number journey. It forces us to question our assumptions about randomness, to consider that even the most unpredictable phenomena might be governed by hidden rules and structures.
It's a humbling thought, but it also makes this exploration all the more exciting. We're dealing with something truly profound, something that stretches the boundaries of our understanding of mathematics and the universe itself.
Exactly. And as we continue our deep dive, we'll uncover even more mysteries, challenge more assumptions, and hopefully gain a deeper appreciation for the incredible power and beauty of prime numbers.
Welcome back to the final part of our prime number deep dive. It's been quite a journey, hasn't it? From primal dyadic maps to prime DNA to these mind-blowing patterns. It feels like we've barely scratched the surface.
It's incredible how these seemingly simple numbers, the building blocks of all other numbers, lead us to these profound questions about randomness, order, and even the nature of reality itself.
Exactly. And in this final part, I want to explore what it all means. What are the implications of these discoveries? Where do we go from here?
Excellent question, because it's not just about abstract mathematical beauty. Understanding prime numbers has the potential to reshape technology, computing, and even our understanding of the universe itself.
Okay, so let's start with those practical applications. We've talked about cryptography, simulations, even artificial intelligence. Can you give our listeners some concrete examples of how prime number insights could revolutionize these fields?
Absolutely. Let's start with cryptography. Right now, much of our online security relies on the difficulty of factoring large numbers into their prime components. But what if by understanding prime DNA, we could create entirely new encryption methods based on the chaotic properties of primes?
So instead of just relying on the difficulty of factoring, we'd be using the inherent unpredictability of prime numbers to create unbreakable codes.
Precisely, we could design algorithms that leverage the chaotic behavior of primes to generate encryption keys that are virtually impossible to crack. It would be a whole new level of security for online transactions, communications, and data storage.
That's incredible. What about simulations? How could those primal dyadic maps and the insights into prime DNA impact our ability to model complex systems?
Right now, many simulations rely on pseudo-random number generators, which aren't truly random, but with prime numbers, we have a source of genuine mathematical randomness that could revolutionize simulations in fields like weather forecasting, financial modeling, even drug discovery.
So by using primes, we could create simulations that are more accurate, more realistic, and better able to predict the behavior of complex systems.
Exactly. Imagine simulating the stock market with unprecedented accuracy, predicting weather patterns with greater precision, or even testing the effectiveness of new drugs in virtual environments that mimic the human body with incredible detail. The possibilities are truly mind-blowing.
And then there's artificial intelligence, this whole concept of the primefold AI, an AI that can decode the language of primes. It's like something out of science fiction.
It might sound like science fiction, but the foundations are already there by analyzing massive data sets of prime numbers. We could train AI to recognize patterns in their digit structure, predict their chaotic behavior, and even design new prime-based algorithms for machine learning and problem solving.
It's like we'd be giving AI a whole new toolbox. A toolbox filled with the most fundamental and powerful building blocks of mathematics.
And who knows what AI might discover with that toolbox. We could see breakthroughs in fields like pattern recognition optimization, even creativity. Imagine AI composing music based on the principles of prime number chaos, or designing entirely new materials based on the hidden symmetries of prime distributions.
It's exciting and a little bit daunting to think about, but those are just the practical applications.
Mm-hmm.
What about the bigger picture? How does all of this prime number research impact our philosophical understanding of the universe?
That's where things get really interesting. If prime numbers are exhibiting these quantum-like behaviors, if their distribution is governed by a function with eerie connections to quantum physics, it raises profound questions about the nature of reality itself.
Are we just seeing a mathematical analogy, or is there a deeper connection between the world of numbers and the quantum realm? Could primes be a bridge between these two seemingly separate worlds?
It's a question that's driving research at the forefront of both mathematics and physics. Some theorists believe that our universe might be at its core a mathematical structure, and that prime numbers are revealing glimpses of that underlying code.
So maybe the patterns we're seeing in primes aren't just mathematical curiosities, but echoes of the fundamental laws that govern our universe. It's a mind-bending thought.
It is indeed, and it suggests that exploring prime numbers isn't just a mathematical pursuit, but a journey into the heart of reality itself. And that journey, as we've seen, is full of surprises, challenges, and a sense of wonder that never fades.
Absolutely. And remember, the Prime Genome Project, we discussed the idea of a global effort to map out the entire computational landscape of primes. It's like a call to adventure, an invitation to anyone with a curious mind to join in this grand exploration.
It's a project that transcends borders and disciplines, uniting us in a common goal of understanding these fundamental building blocks of our universe. And as we wrap up this deep dive into the uncanny world of prime numbers, I want to leave our listeners with a final thought. Never underestimate the power of a question. The most groundbreaking discoveries often start with a simple question.
So keep asking questions and keep that sense of wonder alive. Thank you for joining us on this incredible journey.